Welcome to the fifth part of Building Robots System Integration. My name is Gaspar Škulj from University of Ljubljana, and today we will learn about a wireless control of a mobile robot. We will start with a description of foundations for a wirelessly controlled robot and continue with the information flow for the manual control. And at the end, we will define this week's project assignment. A mobile robot is intended to move in its environment. To achieve this, it needs an onboard power source, actuators, sensors, and a control program. Ideally, the robot would make its own decisions where and when to move based on its task and sensor inputs. To create such a robot, we first make all the mechanical and electrical connections between its numerous parts. Then single or multiple programs are introduced to control those parts. With that, we make information connections. With the programs, we convey how the robot should work and what is its task. Similarly to designing mechanical and electrical parts, the programming of the robot is also an iterative process. Before granting the robot full autonomy, we need to demonstrate manual control. For a mobile robot, it is quite obvious that if we want a manual control, it should be wireless. It is usually just more convenient than a wired control with a cable that can quickly become an obstacle for the robot. In our case, the mobile robot consists of two servo motors, each with 4 modules. First, we made sure that we can use each module's capabilities. On the sensory module Ruby, we learned how to use the ultrasonic sensors and microphones. On the control module Diamond, we learned how to control the DC motor with a feedback loop and consequently the rotation of the drive wheel. With the communication module Sapphire, we learned how the microcontrollers on the modules can communicate among themselves and with other devices. We also know that the robot has its own battery power supply and that modules are connected with CAN bus. Now we want to combine all the modules in a larger system, first a servo motor, then the mobile robot. And we want the user to have a wireless manual control over the robot's movement. To implement the wireless control, we will use Wi-Fi technology because microcontrollers on the modules have Wi-Fi capability, and so do our smartphones and computers. And we want to use a computer or a smartphone as an input device for user commands. To get a better understanding how wireless communication can be used to manually control a mobile robot, we look at the information flow for our specific robot. For another robot, the information flow may be different, however, the concepts will be similar. On one side is a user with a command, and on the other, the robot that will execute the command. The command can theoretically be any information in any form. But we want to pursue design simplicity, and we will send just the 2 numbers that will tell the robot how fast the servo motors should rotate. And now we need to design how that information will flow from the user to the control module on the robot. There are many options how to implement Wi-Fi communication even on our system, and we are looking for one that will best satisfy the following specifications. First, the user input interface should be a web page on a smartphone. We don't want to develop an additional control device or ask the user to install a control program on his device. Second, no additional internet infrastructure should be used, just the robot and the smartphone. Sometimes, additionally needed infrastructure will not be available. If you would rely on a use of a router, that would prevent us from controlling the robot outside in a field. Third, control should feel responsive for the user. If the control has too much delay between input and execution, the user may not be able to control the robot safely. To address the first specification, we will develop a web page that uses a JavaScript library for the command input visualization. The second specification is much more demanding, because if we can't use additional internet infrastructure, that means our devices can connect to a router to communicate and can't use other devices to hold the control web page. There is also no internet access. Fortunately, the microcontrollers we are using on the robot have enough onboard memory to store all files necessary to run the web page, including the JavaScript library. Also, each microcontroller can act as an access point for other devices to connect to. However, number of devices is by default limited to 4 and can be extended to 10. This stresses the access point microcontroller and can cause unwanted delays in communication. This is related to the third specification about responsive control. This implies that update of commands should be frequent and without delay. We can address this by selecting a communication protocol designed for fast exchange of information. In our case, we will use WebSockets, as we don't want to reinvent existing functionality already available with the use of libraries for the website and microcontroller. Manual control of the mobile robot is set up so that the communication module on the right servomotor has the speed references for both servomotors. The communication modules on the right and the left servomotors periodically, every 50 milliseconds, send the current speed reference via CAN bus to the control module. The control module continuously and independently runs the speed control loop based on the received references. For the communication module on the left to be updated with a new speed reference, a connection between the two communication modules has to be established. The communication module on the right servomotor creates an access point on which the communication module of the left servomotor connects to and opens a WebSocket. Both communication modules have a static IP address. The communication module of the left servomotor then periodically, every 50 milliseconds, as a WebSocket client asks for a speed reference update from a WebSocket server on the communication module of the right servomotor. When the robot is so set up, the user with a smartphone also connects on the access point. Then the user with a browser navigates to the communication module's IP. This loads all necessary files from the microcontroller's memory to the browser on the smartphone and opens the control web page with interactive right and left joystick. A WebSocket connection is established with the communication module on the right servomotor. If any joystick is moved, speed references are updated based on joystick positions and set via WebSocket to the communication module on the right servomotor as binary data. If the WebSocket communication is closed, the speed references on the communication module on the right servomotor are set to be 0, thus stopping the robot. Your task for this week is to create a microcontroller program that demonstrates how a wireless control communication that is used to control our mobile robot can be established. Create a program for a ESP32C3 or S3 microcontroller that acts as an access point and responds to a WebSocket connection. Use a personal computer to connect to the access point and use Firefox browser extension WebSocket Wizzo to open a WebSocket. The microcontroller should print out via the USB serial communication in Arduino IDE any message sent from the computer. Ability to wirelessly control a mobile robot is a very important feature for manual and automatic control, and it should be considered early in the development of the robot. information flow should be designed to be fast and robust. It is best if parts of the information flow are independent and can safely handle unplanned events. It is also useful if robot control isn't dependent on the internet infrastructure we can directly control. The example that we studied showed how this could be done for our mobile robot. Thank you for watching.